Example 13.10 asks us to factor g of x, and it also says that we are given that g of 2 is equal to 0. Now, when I see the word factor and I have an equation given to me, I immediately think about my traditional factoring techniques. And with this particular example, I think factoring by grouping. So when I see factoring by grouping, I'm going to take the first two terms and group them together, and the second two terms I'm going to group them together, and I'm going to attempt to go through that process. And g of x would then have, let's see, x squared times 2x minus 5. And then for that second grouping, the only GCF I have is 1. So it's going to be 1 times x plus 2. And the whole purpose of factoring by grouping is so that way you can get a third factor and eventually get the two terms here down to just one big term with factors. But the only way that works is if these two look the same, and they don't. So this is an example where a traditional factoring technique doesn't work, even though we've seen it work in the past. So factoring by group, I'm just going to cross that out. Factoring by grouping is not going to work here. So instead, there must be another way to be able to get the factoring done. Well, we now have seen that division can simulate the factoring for us. So there's an extra piece of given information here that we haven't used yet, and that is g of 2 is equal to 0. So remember that factor theorem said that if we have f of c equal to 0, then, so it says if f of c is equal to 0, then that means that x minus c is a factor. So what we need to do is work this whole process backwards. And we need to think about, okay, if for our purposes we have g of 2 is equal to 0, then that would mean that x minus 2 is going to be a factor for g of x. That's what the factor theorem tells us. But the factor theorem also implies that g of x is going to be factored, of course, as x minus 2, but I'm also going to need a quotient here. And that quotient has to be paired up with this x minus 2 representing the divisor for a division problem. So this is all really high-level concept stuff working with the factor theorem and the remainder theorem all at the same time. So this is an example of a problem that I typically put on exams because it makes you really think about what you're using, what you're doing. So it doesn't just walk you through the process. You've got to think about what you're going to be doing. So this is all kind of just putting my thoughts on paper. Here I want to actually start executing the math. I want to take g of x and I'm going to divide it by x minus 2. And I know that I want to use x minus 2 because g of 2 is equal to 0. And that implies that x minus 2 has to be a factor. So let's let the x minus 2 be the divisor, giving us the problem 2x cubed minus 5x squared plus x plus 2, all divided by x minus 2. So let's go through the division process. I will use synthetic division on this. 2, negative 5, 1, and 2. I will use positive 2 to represent my divisor. Bring down my leading coefficient, and away we go. That'll be 4, negative 1, negative 2, negative 1, negative 2, and 0. So you'll notice here that we've got a remainder of 0. We have the constant next to that, the x coefficient next to that, and then the x squared coefficient is last, giving us a view of the quotient. And the fact that the remainder is 0, that implies that g, we're using g here, g of 2 is equal to 0. But that was already given to us. So this is just a way for us to verify that what we were given is absolutely correct. So since it's correct, we're going to take the divisor, which is x minus 2, and then our quotient, which is going to be 2x squared minus x minus 1, and that is going to begin the factoring process for us. So we're factoring by grouping failed. The remainder theorem and factor theorem, along with synthetic division, will prevail, and it will perform that first round of factoring for us. Now it's up to us to complete the factoring, and this is going to end up being an instance of trinomial factoring. So for factoring 2x squared minus x minus 1, we will end up with 2x plus 1 and x minus 1. And that is the complete factoring of that, g of x, and it is also a linear factorization.